Okay, so in this lecture, we will be talking about an important topological concept and one of the most fine structures, which is an induced topological space called the quotient space. Called the quotient space, and one more term associated with the quotient space is what we call an identification space. Is what we call as an identification space. Clear? So let us first go by the basic intuitive thought process of constructing quotient spaces, and then we will go into the rigorous mathematical statements associated with such quotient spaces. So what we typically do is that we start with an arbitrary figure, or I shouldn't use the term figure, in fact we start with an arbitrary space which is quite geometric in nature, so as to just form a psychological link between the mathematician and the space, because when we talk about arbitrary topological spaces we just talk about arbitrary geometric shapes, right? But if we give some proper known geometric stature to that space we are talking about, then it's sort of pretty easy to visualize and pretty easy to think about such spaces. In fact, these thinkings actually bring out some complicated and some twisted spaces into the hands of a reader or a mathematician, whatever you want to speak of. So the basic thought process we will start with is, suppose I start with a rectangle, or let's start with a square, for example. Let's start with a square. So I consider a simple square. So let me just consider a simple square. Okay, wait a sec. I think I should have some tools. Okay, I am not given these things. Whatever, okay, let me just draw it on my own. Okay, so I have a square, let's say. Okay, I have a square, and these squares I have identified them as a so I have identified this as I cross I, where I is just the interval 0, 1. Clear? So it will give this square to us, and I can consider this typically to be a subspace of R2, but I don't need to consider these things now because I am just talking about an intuitive approach to what actually quotient topology does, or quotient spaces does. So let me just give some coordinates to this. So I have this to be the coordinate 0, 0, this has the coordinate 1, 0, this has the coordinate 1, 1, and this has the coordinate 0, 1, and I am talking about this whole space. So I am talking about whatever inside it as well. Okay, so I start with this figure, and what I'm trying to do is that I want to glue up these two vertical edges. So I want to glue the two vertical edges along the same orientation, So what I do is basically I start with this rectangle and I just twist out the edges. So I just do something of this sort. Okay, so I just start to twist these edges, roll these edges, you might think of it like that. I start to roll these edges of the square, and I bring them together. I bring this edge, so let me just, I bring this edge and this edge together to each other, and I glue them up. So what I will eventually get is like this, some sort of a thing like this, right? So yeah, so if I glue this up, so I'll get a figure some sort of like this. Okay, horrible drawing. Let me try to draw this up. Yeah, so I'll get a cylinder, typically speaking. I'll get a cylinder like this, and this edge which has been glued now, it is somewhere, suppose here, it is somewhere, suppose here. Clear? So what I'm typically doing is that, in a more technical term, is that I am identifying these two edges, or I am identifying any point on this edge, with the corresponding point on this edge. This is what I am typically doing in a more technical term, and in the in a very intuitive process, I can just use the term that I am gluing up these edges. Okay. So the technical term is typically that I start with the point on one of the vertical edges. Say this point is, now what should be the coordinate of this point? So the coordinate of this point should be just 0, y, let's say, and I'm identifying this point with this point, and the coordinate of this point is typically 1, y. So what I'm typically doing is that I am identifying the point 0, y with the point 1, y. This is what I am typically doing, nothing else. Clear? Got it? Okay. So yeah, this is sort of a good thing. Now what I want to do is that I want to continue this process of gluing up things from a square. So let me go back. So suppose I start with example 2. So I start with a square again, and I start with the same square, I cross I. I start with the same square. So I have the same square in hand. Okay, I'm not writing this anymore. Let it be just written as S. Okay. Now what I'm doing is that I am identifying these two vertical edges as I did in the previous example, but with respect to that, I'm identifying two more edges, which are the horizontal edges, and I am also doing that along the same direction. What do I mean by along the same orientation or along the same direction? Is that the identification happens with respect to corresponding points. That is, this is identified with respect to this, keeping the y coordinate constant in this case. So here what I will do is I will choose a point here and identify this with exactly the corresponding point on the other edge, and I'll do the same for the horizontal edges as well. I will choose a point here and I will identify the same with the exact corresponding point on the other edge, right? But clearly doing these two identifications together, or these two gluings together, is not possible. So what we do is that we first glue one of the parts, and then we glue the other part. So see what I can actually do is that, so suppose I first glue out the vertical edges. For example, I first glue out the vertical edges. So I know that I'll get this cylinder. So, but now so let me just go back once. Yeah, but now I have to glue back the upper edges as well. So you can just easily see that these horizontal edges have now become these the circular portions of the top and bottom of the cylinder. So let me just give this like this. Yeah, right. So I need to identify now these two cases, these 2 points, right? And to do that, what I typically do is that I just roll it up horizontally. So I just write it like this. So yeah, you can one minute. So you can just think of it like this. Yeah, so I just place it horizontally. Okay, so yeah, so I have like this, I have like this, and I have like this. Clear? And I have these two cases, right? Okay, this is what you typically will be having. And now it is easy to identify these two. So I need to just glue out these two surfaces which are marked by arrows. So if I glue these out together, what I will be eventually getting is, which can be easily visualized. So I'll get a thing like this. So it's basically a torus. You will get a donut, basically a donut, a circular tube with a hole in the middle, right? A hollow tube. You need to be be reminded of the fact that we are talking about a hollow tube in this case. Everything inside is hollow, whatever we have is on the surface, right? So this is what we call a torus, and it's usually denoted as T2. Clear? Now the thing to observe here is that, which might be a sort of a bit technical to talk about at this stage, but whatever. See, you actually are dealing with two circles in this case. See, you have one circular arc here, which typically is present in this way. You can easily see this out, right? But the vertical edges which you identified, so these appear in this way, and when you roll it up, it will appear some sort of in this way, right? So actually what you are typically doing is that you are kind of forming out the product topology, if you have basic sense of what product topology is. So product topology is basically considering some sort of a direct product of two topologies. Okay, so typically speaking, this torus is what you call in terms of topologies homeomorphic to S1 cross S1, where S1 usually presents the unit circle in a plane. And you can easily observe that all these circles we are eventually constructed here are unit circles, because the square we started with was a unit square. Okay, so this is a more technical thing to talk about, so let us not get indulged into this. I just stated this as a fact, but the most important thing to observe here is that we have actually constructed what we call a torus. Clear? Okay. Now one of the finest figures when you talk about some topological structures or certain important shapes which are very famous, one of them is what you call the Mobius strip, right? What you call the Mobius strip. So what you call the Mobius strip. Okay, now how can you actually construct a Mobius strip? So how it is typically constructed? So suppose I start with a string, a strip of paper. Let's say I start with a strip of paper. Now it's too difficult to give a video description to these things, because I have no access to recording things via camera. But I guess whatever how the way I'm trying to demonstrate these out, you guys should understand what I'm trying to say. Okay, one second, I'm going back to where I was. Okay, right, so I was here. Yeah, so I start with a strip of paper, and what I do is that I want to glue these two edges. So I'm still gluing vertical edges, so I bring them in this way. Okay, so I bring them in this way together, but before gluing them, what I will do is that I will just twist this out. I will just twist this once, and which we often refer to as a half twist, and in some books you also get the referring as a full twist. Okay, so a twist by 180 degrees is typically often referred to as a full twist, or often referred to as a half twist as well. Whenever we will be talking about such twists, we will be we will be not using the word half or full twist as such. If there is some specific angle of twist, I will just mention the angle to get a proper notion of what I'm talking about. So what we do is that we twist out this paper such that so I'm just drawing half the paper now. So this is one end of the paper, this is another end of the paper. So suppose I identify the upper vertex with a red dot and the lower vertex with a blue dot. So what I am doing is that I am twisting this out. So after twisting, the edges will become like this. So this should be very easily observed, that the red dot will come at the bottom and the blue dot will be coming at the top, and then I will be going just gluing this up. then I'll just gluing this up, right? And eventually what you will be getting is, you will be getting a simple strip, in this way, but you have a twisted portion to this, right? You have a twist here. Yeah, so how should I draw this up? So wait, I guess you guys are having a certain visualization of what is happening. So yeah, I think I can draw this in this way. So I have like this, and then yeah, I think I can, yeah, okay, yeah, this will do, right? Okay, this will do. Yeah, so this is the way the strip you are having. This is the way you are having the strip. So there is a certain twist here, a twist, which we, whatever I said, we call it a half twist or a full twist, but this is actually one twist. So you are having one twist. So a strip of paper glued together with one twist is what you call a Mobius strip. Now the concept relies on the fact that how can we construct a Mobius strip using some sort of a quotient topology, which is quite intuitive to guess at least. So we again start with a square. Okay, so again start with a square. It will be better if I start with a rectangle, then it will be more easily visualized. So suppose I start with a rectangle, and so what I do for the rectangle is that I just increase the the Cartesian product of one of the components. So let me just suppose take this horizontal plane to be suppose 0 to 5, and it was 1 as usual. So let this be 1. Okay, let this be 1. Okay, so so what are we actually trying to do is that I need to identify this vertical edge, not with this vertical edge, but with a twist of this vertical edge, right? Right, this will do. So what I am doing is that I am twisting this out. So I am twisting this, I am twisting and then gluing. Got it? I am twisting and then gluing. So if I twist this out, now the construction is exactly how we did this construction, right? Because this strip of paper can be actually considered to be a rectangle. Got it? Clear? So what is the identification taking in this case? So suppose I choose a point here, say, so a point here would be specifically 0, y. Now the identification is not happening immediately with the corresponding point on the other vertical edge, but it's actually happening with the orthogonal point or opposite point on the other edge. That is, if this is 0, y, then exactly the opposite point should be what this should be. So the x coordinate is 5 and the y coordinate must be 1 minus y, right? So I am actually gluing out these 2 points. Is this part clear? Is this part clear? So this will be eventually giving me what I call a Mobius strip. And have I given the relation, the symbolic notation of how we are identifying? Okay, let it be. So I guess this concept is sufficiently clear. Let me just end these examples with a very fine example, which actually seems to be more relatable in terms of the things we have already worked with. Suppose I start with the unit interval. Let me just start with the unit interval. So unit closed interval, so 0, 1. And what I typically trying to do is that I am trying to identify the 2 end points of this interval. I am trying to identify 0 with 1. Okay, I am trying to identify 0 with 1, and see, so this unit interval, if you can think of it like your, so suppose you can assume this to be a string. You can assume this interval to be like a string, and twist it, or I should say twirl it, to make the endpoints. Now what should be the endpoints of the string? That is the points 0 and 1 meet, and that will be exactly gluing 0 and 1. So what I am doing is that I am basically bringing this part here, bringing this part here, making them meet. So I should basically get a circle, right? I should basically get a circle with this point being 1, identified by 1 as well as 0, right? Clear? Okay. So these are the examples which are some of the most interesting examples concerned about this stage of talking about quotient topology. Now what I want to do is that I want to give a rigorous introduction to what quotient topology basically is. Now the introduction can actually be, or the definition of a quotient topology, or the basic discussion about quotient topology can start in two independent ways, but eventually they will meet under a topological equivalence. So let me start with one of the ways, and then we will be eventually getting into the other sort of a definition. Then we will be seeing that how they are actually topologically equivalent. There is nothing different topologically to talk about them. So let us start with the way we started our discussion. Okay, so rigorous identification spaces, or quotient spaces. Okay, clear? So what are we trying to do? First let us so motivation. Given a topological space, we are trying to identify, or whatever the term I used is, or glue two or more points, or two points, let's say. We are trying to glue, we have to identify points of X, given topological space X, with a single point, and these identified points will give rise to a new topological space called the identification space. Clear? So the main overview of this motivation is that we started with a square S, and by identifying this vertical edge with this vertical edge, we formed a cylinder. Now observe that there is a fine line in this cylinder, and this line is actually what identifies both of these vertical edges. So what I am trying to actually do is that I am actually identifying. You can easily observe that, suppose I choose a point out from here, I choose a point out from here. So both these points are actually identified by a single point here, right? Because if I am actually collapsing both these edges to a single edge, so 2 points on these edges, 2 corresponding points on these edges is identified by a single point on this edge, right? And collection of all these single points will form this line. And what I am trying to say is that I am constructing a new figure out of this figure by identifying two distinct edges into a single edge, and this gives rise to a new topological space. Now clearly enough, this was already a topological space if you consider this to be simply a subspace of R2. What we want to do is that we want to identify this as a topological space, and for that we need to define a topology on it. But in order to define a topology on it, we need to do something more. The thing to observe here is that the sort of deformation we are making. So what are we actually trying to do? Visually, we started with some subspace, with some space, some topological space, and we are actually deforming the space into a new space. We are sort of deforming a geometric object into a new geometric object. Okay, and to keep topological equivalence of these two spaces, or sort of, if I don't use the technical term topological equivalence, what term can I use? Yeah, to keep an analogy between both these spaces, that at least I can look at both these spaces and see, and some sort of I can identify that, yeah, this cylinder has been constructed from a square. Some sort of, that is what I am trying to speak. Suppose I start with a square and I just crumble it up. What I am trying to say, that I start with a square and just crumble it up. I am not that sure whether this crumbled up paper has originated from a square or not, but if I start with a square, I gently fold it down into a cylinder, I am almost 99% sure that I have started with a square to form the cylinder out. I think I try to make a little bit of sense what I am trying to say. What I am actually, a more technical way of what I am trying to define is a continuous deformation. Okay, so what we are trying to do is that we are trying to continuously deform this square into this cylinder, and this continuous deformation, you can sense it as a gradual deformation. Whatever you are doing is a smooth way of deformation. Whatever you are doing in a smooth way. Okay, there is no the sudden shocking sort of an action taking place with this deformation. Whatever is happening, it's happening very gently, in a very smooth manner. Such sort of deformations you can sense as a continuous deformation. Therefore, what I'm now these things are making some sort of a sense. So suppose I start with, so I am trying to generalize this out. So suppose I start with some point, some topological space X, and I identified points inside X, and I formed a new set Y, where the identified points correspond to the points in Y. I guess now I am making some sort of sense, because, okay, let me give a visual interpretation once more. I started with this square, so the points on these two edges are identified with this single line, and every other point is identified arbitrarily with points on the cylinder, right? There is no so every point here will go to a unique point on the cylinder outside this line, which is quite obvious. So every point you take here, it will go to a unique point on this cylinder, right? I guess I am now making some sort of a sense. So and what I can try to do is that each of these points which are not on these vertical edges, I can just send these points to themselves. I am writing the notation on the right hand side a bit later, and whatever points I have on these vertical edges, I can send this to this line, or the points which have formed from the identification of these points. Before that, I actually need to make a bit more sense. Okay. So we identify these points specifically using an equivalence relation. Now it will be a bit clearer. Using an equivalence relation. Okay. So what are we basically trying to do? Consider this example of a square transformed to a cylinder. So I choose a point. So this how was the square designed? So the square was designed as, so S was designed as I cross I, or which I can write as 0 1 cross 0 1, which I can also write as simply the set of points x y such that x is less than equals to 1, greater than equals to 0, and y is less than equals to 1, greater than equals to 0. Right? Right. Okay. So this makes sense. Now So what I'm trying to do is that I need to identify points on the vertical edges. So consider the relation, this on x as, so we are defining this relation as, so what are we trying to do? We are trying to identify a point on the left vertical edge with the corresponding point on the right vertical edge. Any point on the left vertical edge will have the coordinate of the form 0 y, and we are relating it to the point 1 y. I guess this made sense, right? And these y varies from 0 to 1. Clear? And every other point is just identified with itself, right? Every other point is just identified with itself. There's nothing complicated to talk about in that case, right? So yeah, okay, so how should I write it out? Yeah, every other point, say xy, is identified with itself, where x is less than 1, greater than 0, and y is as usual less than equals to 1, greater than equals to 0. Okay, this is what we are trying to do. Okay, so now this relation will form a partition on x, right? It will form a partition on x. So so I am identifying this square as x. So now let me write this x as some arbitrary topological space. It will be more clear if I draw it like this rather than drawing it to be a square. And see, there will be exactly two such partitions, right? So one partition where you have those singleton points. See, observe that what are the only possible equivalence classes in this case. So if I consider the equivalence classes of points where x is in this range, so it will be just the singleton set xy, right? And if I consider equivalence classes in this case, then what should be it? So if I consider this, then it should be exactly equals to 1y. So each such equivalence classes which consists of 2 points, typically speaking, 0y will consist of 2 points, 0y and 1y. Clear? Clear? Right. So what I'm trying to do is that now actually let me make this part a bit more general. Okay, let me make this part a bit more general. So definition, let x be, or I shouldn't use the word definition. So let x be an arbitrary topological space, and let this be an equivalence relation, defined on x. Okay, so consider the partitions on x induced by this relation. So suppose this was x, so I have got, suppose, these sort of partitions on x induced by this equivalence relation, and what I'm trying to do is that I am trying to identify each such subset of this partition by a single point, say y1. For example, I identify this with some point y2, and so on, and I identify this with some point yn, and I find a collection of all these points y. This y is typically noted as like this and is called the quotient topology. Induced by x and this relation. Clear? and I hope this way out of identifying a collection of points is clear in this case. So what are we actually doing? If I go back to the definition of cylinders, squares from cylinders, so if I start with the point say 0 1, I consider the equivalence class of this point 0 1, so it will consider the points 0 1 and 1 1, right? So both these points will go to a single point, right? So if I come back here, so suppose this is S, the square S, and suppose this is the cylinder, this is the cylinder. So suppose I have these points, so as I gave the example, I have the point 0 1, and in the same partition I will also have the point 1 1, because they both are identified together, right? The points which are being identified together, if I talk in terms of this equivalence relation, the points which are being identified, they are falling in the same equivalence class, and each subset of these partitions are simply these equivalence classes. So 0 1 and 1 1 are in the same equivalence classes. These are the only elements in these equivalence classes. What I am trying to do is that I am mapping 0 1 and 1 1 to a single point. Similarly, if I start with a point, let's say say 0.21, then it will get mapped to, sorry, 0 1 0.2, I'm sorry. So yeah, it will be, sorry, 0 0.2, then it will be mapped to 1 0.2, right? So I will get mapped these two things to a single point here. And if I start with a point where x is suppose so x is suppose 0.5, that is x is neither 0 nor 1, and y is anything, then it will eventually get mapped to a single point, which is itself. But the problem here is that we are actually mapping 2 points to a single point, and how is the way out to do so? Now you can easily observe out that I can actually consider these identifications as a map. How do I consider that? So I consider a map pi from the topological space we started with to this space y, which is basically the identification space or the quotient space of x, and we have already discussed how the identification space actually looks like. So the identification space is actually a collection of the subsets which form a partition of x, where each subset is identified to be a single point. That's exactly how the identification space is defined. So let me first give the intuitive definition, or rather the explained definition of the identification space. So definition: let X be a topological space, let X be a topological space. The identification space, the identification space of X is a space. In fact, we don't even require the concept of an equivalence relation to define an arbitrary identification space, because all actually what we need is a partition, right? What we actually need is a partition, and we can simply define 2 points being in the same partition to be identified together, right? So the identification space of X is a space Y, which is a collection of all subsets of X forming a partition of X, where each of these subsets resemble a point of Y, right? And that is exactly what we had explained here. So each of these subsets are being identified by a single point of Y, right? And so what should be the way out to do so? Now, intuitive enough, since we started the discussion using equivalence relations, and we actually can do this in terms of equivalence relation in a way that, see, the equivalence relations concept can be actually brought into discussion starting with a partition as well. If I start with a certain partition and I say that two elements are related in the very set if they fall in the same partition, it will eventually give rise to an equivalence relation. So starting the discussion with in terms of an equivalence relation or starting in terms of partitions are actually same, right? So what I can actually do is that I can actually talk about equivalence relation on X. Specifically what I am trying to do is that I am trying to consider a map from X to this identification space Y. The symbol Y I will be using for giving the identification space. So pi is a map from X to Y, where I send every element small x to the equivalence class of this under this relation tilde. Clear? Or what I can do is that I can send X typically to the subset which consists of X or which resembles the equivalence class of X in terms of partitions, or to the subset in which X belongs, the subset which forms a partition of X, and that subset. So these are constituting the points of Y, the points of Y. So Y is typically a collection of equivalence classes. Clear? Okay, so that's all for today. In the next lecture we will come up with the other definition of quotient topology, and then we will be binding them all together, and the things we will be then discussing is how we constructed out these torus, cones, so on and so forth. Okay, so meet you guys in the next lecture.